So we continue our solving equations review with these basic trig equations, okay? And what you'll find with these trig equations is there's really two different types. There's ones that require exact solutions, and there's one that require approximate solutions, okay? So the ones that require exact solutions in this particular um, set of problems are 1, 3, 5, and 7. And the reason that these require exact solutions is that these values, sine x equals negative radical 3 over 2, cosine x equals negative 1 over the square root of 2, right after you divide by square root of 2, tangent of x equals negative 1, and secant of x equals the square root of 2. These are all trig wheel values, right? So if we do the unit circle, right, they would all be values that would appear on the unit circle. So these are ones that we could have actually gotten exact solutions for. All right. So what you do is so with number one, it's really just saying, all right, well, sine x equals negative radical 3 over 2. Well, I know radical 3 over 2, the sine of pi over 3 was the square root of 3 over 2, right? If you remember from your table or whatever you wanted to memorize, trig wheel or table, whatever you did, that the sine of pi over 3 was actually equal to the square root of 3 over 2. So that was your first quadrant angle, right? That was this angle in the first quadrant. But since in this case it's negative radical 3 over 2, you need the corresponding angles that pi over 3 is equivalent to in the third and the fourth quadrant, right? So in the third quadrant, pi over 3 is actually going to be 4 pi over 3. And in the fourth quadrant, pi over 3 is going to be 5 pi over 3. So the solutions to this equation here are going to be 4 pi over 3, 5 pi over 3, right? Because again, you were looking for where sine is negative, and sine is negative in the third and the fourth quadrants, right? So I identified the reference angle as being pi over 3, but I needed the angles in the third and fourth quadrant that had pi over 3 as a reference angle. And those are 4 pi over 3 in the third quadrant and 5 pi over 3 in the fourth quadrant, right? So that's how I came up with my solutions. Now the idea though of this is you need what they call general solutions here, because what can happen is, all right, just because I have this angle, all right, that's fine. But what happens when I wrap around the circle again? I get back to the same place. And again, I get back to the same place. And in the reverse direction, same place, same place. So I keep wrapping around the circle to get more solutions. So what I would do is I could add 2 pi any number of times to 4 pi over 3 and get the same value, right? And the same thing with 5 pi over 3, right? I could add 2 pi times any value, times any integer, right? And arrive at the same solution. So this is how you wrote the general solutions, right? 4 pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k. All right. And then you're going to get similar thing with number 3, right? So number 3, you're looking here at cosine of x, right? So you would just divide by the square root of 2. So here you would end up with the cosine of x equals negative 1 over the square root of 2. But you probably remember that negative 1 over the square root of 2, if you rationalize it, it becomes negative square root of 2 over 2. And that's probably a more familiar form for you, right? So again, now thinking unit circle, right? So on the unit circle, we knew that the cosine of pi over 4 was the square root of 2 over 2. So pi over 4, in this case, this is our reference angle. But then again, looking at ASTC, right, where is the cosine negative? The cosine is going to be negative in the second and the third quadrant, right? So we need the angles in the second and the third quadrant that have a reference angle of pi over 4. So in the second quadrant, that would be 3 pi over 4, and in the third quadrant that would be 5 pi over 4. And then again, similar to what we did before, if that's a solution, I can keep wrapping around the circle in either direction. So my general solution would be that plus 2 pi k. And for 5 pi over 4, same thing. Keep wrapping around the circle in either direction. And I come up with 3 pi over 4 plus 2 pi k, 5 pi over 4 plus 2 pi k. So continuing with our trig equations that yield exact solutions, we can look at 5 and 7, right? So in number 5, I had mentioned this, I guess, previously. You would subtract 4 and divide by 4, so you'd end up with the tangent of x equals -1. So tangent's a little different, and we'll look at this in a second. So when is the tangent equal to -1, right? So if you remember, the tangent of pi over 4 was actually 1, right? So again, if we look at ASTC, we're looking in the second and the fourth quadrant, right? Because we want it to be negative. So if pi over 4 is the reference angle, right, we need pi over 4 in the second quadrant and in the fourth quadrant. So in the second quadrant, it would be 3 pi over 4, and in the fourth quadrant it would be 7 pi over 4. And then just as we did before, you get this whole wraparound idea, right? So these solutions keep appearing every 2 pi in each direction. So that's fine and dandy. But what you might have remembered is, hey, tangent really had a period of pi, not of 2 pi, right? So if you just think about this, 3 pi over 4 and 7 pi over 4 actually differ not by 2 pi, but they differ by pi, right? So I can actually combine these two solutions into just one single solution, 3 pi over 4 plus pi k, right? So it's just a more compact way of writing that solution. Now, if you always want to think of, all right, two solutions and then I'm going to add 2 pi k to it, that's fine. But it's actually easier with tangent to remember that, well, tangent, each value has one solution, right? Each value yields one solution, and then I'm just going to add pi k to that solution instead of 2 pi k. So then you don't even really have to worry as much about the other quadrant, right? It's either going to be in the first or second quadrant, and then I'm just going to add pi k to that. So in this case, I get 3 pi over 4, which was the second quadrant, and then I add pi k. So you can pretty much eliminate the third and fourth quadrant, because that'll take care of itself by adding pi k. So that's just something to remember for the tangent. And then with secant, the idea here is you want to think of secant as the reciprocal of the cosine, right? So 7 actually becomes very similar to number 3 if you think about it, right? And that's why it's good that's right next to it, because if we have secant x equals radical 2, you're basically thinking of taking the reciprocal of each side of this. So the reciprocal of secant is going to be the cosine of x, and the reciprocal of square root of 2 is 1 over the square root of 2. So it actually ends up being almost identical to equation 3, except that it's positive instead of negative, right? So cosine x equals 1 over the square root of 2. Remember, we had thought of this as the square root of 2 over 2 when we rationalized the denominator. So this one, we remember the cosine of pi over 4 was the square root of 2 over 2. So pi over 4 was my reference angle. But again, ASTC, now here I'm looking for when it's positive. So I already have my first quadrant angle, right, which is pi over 4, but cosine is also positive in the fourth quadrant. So in the fourth quadrant, it would be seven pi over 4. And there is another way of looking at that also, which I won't do in this video, but you can also think of the fact that cosine is what we call an even function. So once we have one solution, right, which in this case was pi over 4, the other solution is just the opposite of that. So the other solution would have been negative pi over 4. But hopefully you see that negative pi over 4 is really the same as 7 pi over 4. I won't get into details with that, but if you're curious, ask me about it. All right, because that can be helpful when doing cosine problems if you just realize that it's an even function. All right, but we get pi over 4 plus 2 pi k and 7 pi over 4 plus 2 pi k.